Welcome to the deep dive. Today, we're tackling a really critical decision for anyone machining parts, choosing the right CNC lathe.
Absolutely.
Get this wrong, and honestly, you're looking at wasted time, maybe scrap parts, and yeah, a serious dent in your wallet.
Definitely.
So our mission today, to arm you, the listener, with the essential knowledge of workpiece features, the things that should be non-negotiable when you're selecting a CNC lathe.
Exactly. We're aiming to cut through some of the jargon, really get to the core of what truly matters for your machining success.
Right.
It's not always about the flashiest features. It's about deeply understanding your parts and matching them to the right machine capabilities.
And we've got a pretty solid set of criteria we're going to explore. We'll be digging into maximum swing diameter and, crucially, the maximum actual turning diameter. And understanding the difference there, well, that can save you a lot of grief.
It really can. It's a common trip up.
We'll also cover maximum turning length, the kinds of materials you'll be working with, the precision level you need, your expected production volumes.
Yeah, and the basic shapes, too.
Exactly, the general part type.
Yeah.
Are they more like wide discs, or maybe short, stubby shafts, or those long, slender rods?
Understanding these terms in detail isn't just academic. It's genuinely your first line of defense against, investing in a machine that simply can't do the job you need it to.
It ensures that lathe you choose can actually process your parts efficiently.
Yeah.
And accurately.
Precisely.
Okay, let's dive in. First up, maximum swing diameter. When you see that on a spec sheet, what does it actually mean in practice?
Okay, think of maximum swing diameter as basically the absolute largest circular space a workpiece can occupy while it's spinning in the spindle.
Okay.
Without hitting any part of the machine itself, the bed, the covers, anything. So it's like your ultimate, will it fit? Check.
So if your raw material, like before you even cut anything, is wider than this number.
It's a non-starter. Exactly. You might also see terms like swing over cross slide or swing over carriage.
All right.
Those are usually smaller numbers because, well, the cross slide and carriage components sit closer to the center line. But the main max swing is about that raw physical clearance.
So even a weird shape, like a casting with a lump on the side.
Yeah. Imagine a flange casting with an odd boss sticking out. That total diameter, including the boss, has to fit within that max swing dimension. Otherwise, you can't even mount the thing.
Right. So it's purely about physical rotation space, not about cutting yet.
Exactly. It's the initial, can I even get this in the machine? Check.
Yeah.
Especially important for those wide disc type parts.
Right. That makes sense. Physical fit first. Now, the next term, maximum turning diameter, sounds really similar. This is where people get confused, isn't it?
Absolutely. It's probably the most common point of confusion. Max swing tells you what can physically rotate.
Right.
But maximum turning diameter tells you the largest diameter the lathe can actually machine effectively with its cutting tools. Ah, okay. So it's about the cutting action.
Precisely. Think of it like this. The swing is the size of your garage. The turning diameter is how wide the garage door opens, maybe? Or how much space you have to actually walk around the car and work on it once it's inside.
Gotcha. So the tools need room, too.
Exactly. It's almost always smaller than the max swing because you need clearance for the tool holder, the turret itself, maybe the guide rails.
Interference potential.
Right. These components can interfere if you try to cut right out to the maximum swing limit. So the maximum turning diameter, sometimes called maximum machinable diameter, that's your practical upper limit for cutting.
And that's limited by how far the tools can move.
Yeah. Primarily by the x-axis travel. That's the tool moving in and out, towards or away from the workpiece center and avoiding collisions during the cut.
Okay, so give me an example.
Sure. Let's say you've got a, 400 millimeter piece of stock. The lathe might have a max swing of a 400 millimeters, so technically it fits.
But if the max turning diameter is only a 350 millimeters, you physically cannot machine that entire 400 millimeter diameter down. The tool just won't reach that far out safely or effectively.
Right, restricting the finished part size you can actually produce.
Exactly. So if you're doing large diameter, maybe thin parts like big flanges, you need that larger turning diameter.
Makes sense.
But there's a trade-off. Machining really close to that maximum turning diameter can sometimes reduce rigidity a bit. You might need to back off on speeds and feeds.
Ah, impacting efficiency.
Potentially, yeah. Conversely, if you mostly do smaller, slender shafts, a machine with a smaller turning diameter could be perfectly fine and likely more cost-effective for you.
Okay, swing is fitting, turning diameter is cutting. Got it.
Okay.
That distinction is super important. Now let's talk length. Maximum turning length. I can just imagine the frustration. Getting a part that's just a tiny bit too long.
Oh, it's a classic problem. And usually avoidable with proper planning. Maximum turning length specifies the longest workpiece you can machine along the z-axis.
That's the axis parallel to the spindle, right?
Yeah.
Lengthwise.
Exactly, the maximum length you can machine in a single clamping without having to reposition the part. And remember to account for chucking material, not just the finished length.
So what defines this length? The bed.
It's determined by a few things. The physical length of the bed, sure, but also the position of the tailstock if you're using one.
Which you often need for longer parts.
Right, for support. And also the total travel range of the tool post along that z-axis. It's often defined as the maximum distance you can get between the spindle nose and the tailstock center, or sometimes just the max z-axis travel spec.
And if your part is longer than that?
Well, you simply can't machine the whole length in one go. You're looking at multiple setups.
Which sounds like a recipe for increased errors, not to mention time and cost.
Absolutely. Think about an 800 millimeter long shaft on a machine with only 500 millimeter turning length capacity. You'd machine maybe 500 millimeters, then unclamp, carefully shift it, reclamp, try to blend the cuts.
Ooh, nightmare.
It introduces significant time, complexity, and a huge potential for misalignment or accuracy issues where the cuts meet.
And you mentioned support.
Crucial for longer parts, especially slender ones. A tailstock provides end support. But for really long, thin parts, you often need more. You'll need the ability to use steady rests or follower rests.
To support it mid-span.
Exactly, to prevent vibration, chatter, and deflection while you're cutting. So ensuring your max turning length comfortably exceeds your typical part length is just vital for efficiency and accuracy.
Okay, that makes perfect sense. So we've got a handle on the dimensions swing for fit, turning diameter for cutting capability, and turning length for, well, length. But you mentioned earlier that the type of part itself really dictates the best lathe. You categorize them as discs, short shafts, and slender shafts. Why is that breakdown so important?
Because it's a really common mistake to think one size or one type of CNC lathe can just efficiently handle everything. It usually can't. The fundamental geometry of your typical workpieces.
Disc, short shaft, slender shaft.
Right. That, combined with the material you're cutting, the precision you need, the volume you're producing, all these factors place very different demands on the lathe. It impacts everything. The diameters and length you need, the spindle power and torque requirements, how rigid the machine needs to be.
Automation features, accessories.
Exactly. All of it is influenced by the kind of parts you primarily make.
All right, let's break those down then. Starting with disc-shaped workpieces, things like flanges, big gear blanks, maybe end caps. What are the key specs for those?
Okay, for discs, the defining feature is that large diameter compared to a relatively short length or thickness.
Right.
So your top priorities when choosing a lathe are going to be a large maximum turning diameter and, of course, enough max swing to clear the raw part.
Makes sense. What else?
Rigidity is huge. These parts can be heavy, and facing across that large surface generates significant cutting forces. You need a really stable, rigid machine bed and structure to minimize vibration and maintain flatness accuracy.
And power.
Usually moderate to high spindle power. You're removing material across a wide area, especially during facing. And if you step up to tougher materials, like certain alloys, you'll definitely need even higher spindle power and, crucially, torque.
Okay. What about precision?
If you need tight tolerances on flatness or parallelism on those big faces, then you need to look for machines built with high-quality guideways and just overall robust, precise construction.
Got it. Strong, stable, powerful enough for wide parts. Okay, what about the next category? Short shaft workpieces, like gear shafts, maybe smaller motor shafts.
Right, short shafts. These tend to have a more balanced diameter-length ratio. They're often fairly compact, but can have multiple, often intricate features machined along their length.
So what's key here?
Here, you're looking for a good balance between the max turning diameter and the max turning length. Versatility is often good. A flexible tailstock that's easy to position is usually a big plus for supporting various lengths.
And precision needs.
Often quite high on these parts. You might have bearings, fits, gear seats, threads. So good inherent machine precision is key. Look for things like high-resolution encoders for positioning accuracy, maybe thermal compensation systems to handle temperature changes during longer runs.
What about production volume?
Good point. If you're making a lot of these, efficiency becomes critical. So think about fast tool changes, a quick turret index, and consider automation. Bar feeders for continuous material loading or even robotic loading unloading systems can make a huge difference for high-volume short shaft production.
And spindle power.
Needs to match the material and the typical depth of cut, as always. Maybe not as high as for massive discs, but needs to be adequate for the job.
Okay, so balance and size, focus on precision and automation options for volume.
Right.
Final category, those long, slender shaft workpieces. Lead screws, long hydraulic rods, things like that, the ones that seem like they could easily bend.
Ah, yes, the slender shafts. For these, maximum turning length is, well, it's absolutely paramount. The machine has to accommodate the full length easily in one setup.
Non-negotiable.
Pretty much. And perhaps even more critical here is the machine's overall rigidity and its vibration damping capability. These long, thin parts are incredibly prone to chatter and deflection during machining.
Which ruins the finish and accuracy.
Totally. So you need a really robust, heavy, well-damped machine structure. Essential accessories are also key here. A heavy-duty tailstock is a must for good end support.
And those rests you mentioned.
Absolutely vital. The ability to use center rests, sometimes called steady rests or follower rests, is critical. These provide support at points along the length of the shaft.
Preventing that bending and vibration mid-cut.
Exactly. Without them, machining long, slender parts accurately is often impossible. Material matters too. Tougher materials require even more careful cutting parameter control to avoid issues. And obviously, precision for straightness and consistent diameter along the entire length is usually a major requirement.
So for slender shafts, length capacity first, then extreme rigidity and damping, plus those essential support accessories like steady rests. Wow, okay, this has been incredibly helpful in seeing how those basic specs really connect directly to the type of parts you're making.
That's really the core message here. Choosing the right CNC lathe isn't about just finding the biggest machine or the one with the most features listed.
Right.
It's about a careful, considered alignment. Matching the lathe's fundamental capability swing, turning diameter, length, power, rigidity, precision with the specific geometry, material precision needs, and production volume of the parts you plan to machine most often.
Getting that alignment right is key.
It's the absolute key to maximizing your efficiency, ensuring part accuracy, and ultimately running a successful and profitable operation.
Fantastic. You've given us and our listeners a ton of practical knowledge today. And just to wrap up, here's a final thought for you listening. As you weigh these specifications, don't just think about the parts you're making right now. Take a moment. Think about the future. Are there potential new jobs, different part types, maybe tougher materials you might want to tackle down the road? How do those future possibilities maybe shift or refine what your ideal CNC lathe looks like today? It's about meeting current needs, sure, but also setting yourself up for what's next. Thanks for joining us for this deep dive.